Welcome everyone to our afternoon session. And I'm very pleased to introduce our speaker, Professor Marina Vanucci from Rice University. And she's going to talk about wavelet-based Bayesian estimation and some applications to fMRI data.
Thank you. So apologize, I have a cough, so I may have to interrupt if I start coughing. Hopefully I will not. So I've prepared a talk which is a little bit tangential to the work that I'm doing right now. I used to do a lot of work in wavelet-based statistical models, and I did some time ago I did some work on long memory models, and I proposed a method for detecting change points in the long memory parameter. And so I'm going to describe that work first, and then I'm going to try to link some of that work to more recent stuff that I'm doing, which has to do with the modeling of fMRI data. In particular, we'll be able to use the long memory structure of an error term and the wavelets also in the model, a regression model that I will be using for that type of data, but not the long change, the change point method. So, so essentially, I went through the outline of the talk. I'm going to give introduction to long memory processes. We're going to look at long memory from the point of view of wavelets and what happens if you transform a realization from a long memory process using wavelet transforms. And in particular, we are going to see a property of the wavelets, which is a decorrelation property, meaning that the wavelet coefficients or the data transformed in the wavelet domain are going to be less correlated than the original data. And then we're going to exploit this within a statistical framework to make some modeling assumption. And then, as I said, I'll show an application to the estimation of change points in the long memory parameter, and then we'll switch gear and move to the application to fMRI data, regression models with long memory errors. So, so a long memory process is characterized by non-negligible dependence between observations which are very distant from themselves. I'm sure this audience is very familiar with processes like the fractional Brownian motion or even the fractional Gaussian noise. Fractional Brownian motion is a very well-known example of what we could call a continuous time long memory process. Today I'm going to focus more on discrete time long memory processes, in particular with these RFEMA PDQ models, and I think I have a definition later on in the slides. I'm going to focus my attention on wavelet-based approaches to the analysis of data from a long memory process. And again, I'm going to try to describe in kind of very, very easy way, exploratory way, this property of wavelets that we call the decorrelation property. And we're going to see in particular how it applies to data from long memory processes. The property means, as I already anticipated, that essentially if you have a realization from a long memory process, you take a wavelet transform of your data, you get wavelet coefficients, and this will be nearly uncorrelated, although they come from data that come from a long memory process. And so in that sense, for a statistician like myself, wavelets become a useful tool to simplify the likelihood, because at the point if you model your data in the wavelet domain, you can make some simplifying assumptions. I'm just going to tell you a little bit about wavelets and show you this idea of decorrelation mainly by looking at a couple of graphs, but there are some kind of more rigorous and theoretical studies of these properties, in particular for the fractional Brownian motion and the fractional Gaussian noise processes. And you have here a couple of references. Those are, I believe, papers published in the IEEE literature. So I have 2 or 3 slides on wavelets, because I wasn't sure whether the audience would be familiar with wavelets. Oftentimes we introduce wavelets by comparison with Fourier transforms and Fourier bases. And so if you have a signal like this, or a function that you're trying to approximate, with the Fourier transform, we will use a basis of functions to approximate your signal that are essentially sine and cosine. So they are periodic functions. They have different frequencies, but they are, we say, not localized in time. So they are periodic. They never die along the real axis. With wavelets, we're able to construct a basis of functions which are both, that can be both localized in frequency, like the Fourier basis, and in time. Okay? So the basis functions, the functions that compose your the basis that you're going to use to approximate the signal, can be localized in time. They are essentially small wave, therefore the name wavelets. Okay, they oscillate, so they are waves, but they are wavelet, small waves, because they decay rapidly to zero, or in some cases they are exactly zero outside a certain interval. And so with wavelets, we can vary both the frequency and the band, the location of the basis functions. And so essentially you get what we call a time scale analysis or a time scale decomposition of this signal, unlike the Fourier transform that only allows you to get a frequency decomposition of the signal. So mathematically, how can we construct, right, the basis of functions that look like this? The construction is simple in a way. We start from one wavelet, from one function that we call the mother wavelet, and then we simply dilate or compress that function and translate the function along the real axis. And mathematically, we can do this by introducing two parameters. I'm jumping right away to the discrete construction of the wavelets. There is also a continuous way of doing this. But so in the discrete construction, we introduce two parameters, J and K. J is the scale parameter, and K is the translation parameter. So via J, we can dilate or compress the mother wavelet, and via K, we can move translate the function along the real axis. We impose certain mathematical conditions on the mother wavelet. This is a simplified version of it. Essentially, we impose that the function has to oscillate, so it has to be a wave, but the integral has to be zero. Okay? And this means that it has to decay outside, it has to decay to zero outside a finite interval for that to happen. So this is indeed a wavelet. And then the family of functions that we construct by this mother wavelet will be a family of wavelets. If you're interested in the history of wavelets, probably everybody knows that this was the very first paper by Grossman and Morlet on wavelets. They constructed the continuous version of this construction that you see here. And then another very famous name in wavelets is Dobschi. Dobschi worked with the discrete wavelets, and she was able to prove a lot of nice properties. I'm not going to go into the details of that at all. So then the idea is simple. So now, given our functions, so going back to my plot here, so we have a signal that we want to approximate. We have constructed a basis of wavelets. It is orthonormal. I mean, it has a lot of very, very nice mathematical properties. And so we can construct an object that we can call a wavelet series in this way. Oh, yes. So I get a break.
Sorry?
So I can get a break.
I'll
It's
give
nice.
you a break.
Go ahead.
Okay. Going back to the one which shows, well, first of all, this one, you have one single wavelet form there.
Uh-huh.
And in its transformations, for instance, the positive excursion is a fixed ratio to the negative excursion. If we go back to the one before, you now have several different shapes which look as if the excursions are not related in this way and with different numbers of oscillations. Now this one implies that you have some kind of pool of wavelet forms to take from. How do you define that?
So in this particular construction, you choose your mother, okay, and then you simply define a family based on this function, and you have a kind of normalizing factor here that helps making things work. Yeah. And these are the wavelets that I'm going to use for today.
Yeah,
there are a lot.
The question I was really asking is, what is the ensemble of wavelet forms which you use?
So the ensemble, the family will be for J and K that vary in Z.
So that has a fixed form?
Yes.
Whereas in your preceding slide, they had different forms.
Yeah, okay, it's probably the figure is not, I mean, this one doesn't want to be precise.
But you're only going to talk about one fixed form?
Yes.
Okay.
Okay, so given this chosen family of wavelets, then we can construct a wavelet series of this type. And so the wavelet series will depend on some coefficients that we can call wavelet coefficients. And so in particular, this coefficient here will capture the features of our function f or our signal f at location k scale j. And then by vary k and j, you can capture the different features of the signal or the function at different scales and different locations. And so this way we obtain what we call a time frequency or time scale decomposition of the function. And it has a lot of nice properties. So I already mentioned the fact that wavelets can be localized both in time and in frequency, so they die rapidly at zero, both in time and in frequency. And this is very useful for, I guess in general, for compression of signals, and in particular for compressing and describing signals that may have features like non-stationarity, okay? Because it's well captured by the behavior of the wavelets and also sparsity. This is a multi-scale decomposition, as I already said. It's also something that we can easily implement because instead of having to calculate all these coefficients, where each coefficient would be an integral, it's possible to see if you just, if you think about how you have defined your wavelets, it's possible to see that there are recursive relationships among the coefficients of this wavelet expansion, this wavelet series. And so essentially, you can take advantage of these recursive relationships and essentially avoid the calculations of many integrals simply by using these recursive relationships. Again, because this talk is not primarily on wavelets, I'm going to skip a lot of details. Okay. So they're a nice mathematical object. They have a lot of nice mathematical properties, but they're also nice for real applications because they can be used in particular challenging problems, and they are also very easy to implement and very efficient to implement. In practice, in application, we, as statisticians, we never work with a continuous function of this type, right? But what we observe are data as, say for example, a time series, if I'm looking at x as the time. Okay? So what we observe in reality is a number of observations from that function. And so say yi is my time series data as a time series of observations on the function f observed at a set of n time points, which I'm going to assume are going to be equi-spaced. Okay. And I'm also going to assume that m is a power of 2, although this is an assumption that can be easily relaxed. We can also work with that assumption, but it's a little bit more challenging. So now, once I have data that I observe, my observed time series, then I can apply a discrete wavelet transform to the data that essentially will allow me to calculate discrete approximations of the wavelet coefficients at a number of different scales. And the number of scales depend on how finely I have observed my function f. Okay? So if n is 2 to the j, then I can calculate wavelet coefficients at the all the coarser level coarser with respect to j. And I think, okay, so graphically, again, because I said that there exist recursive relationships among the wavelet coefficients, I don't have to calculate anything particularly difficult, but just apply those filters to the data. So if this is my observed data, I will apply a low and high pass filter, and I will get a decomposition of the data at a lower scale. And I will have some details, what we call details at that scale, and some coarser features of the data. And then I can apply again the recursive filters at this lower level and get 2 levels down, where again I have my features, local features of the data at that level, plus the average or the coarser features, and then I can go down again. And because of the recursive relationships, at every level I lose half the data points, and that's why I can only go down a certain number of scales. Okay. So in practice, we have our data, again, a time series data for us. We apply a discrete wavelet transform to the data. It happens by applying a set of recursive filters. In practice, it gives me a vector of wavelet coefficients, which is composed by a number of sub-vectors that are wavelet coefficients describing features of the data at a given scale. And I have, I can go down for j-1 levels from the data. In these models that I'm going to describe, I'm going to refer to this operation, the discrete wavelet transform, as a simple matrix product of this kind. And indeed, if you write down the algebra and the recursive relationship, it's possible, having chosen the wavelet mother and the wavelet family, it's possible to really write down the form of this W matrix. And the discrete wavelet transform is equivalent to pre-multiply the data by W, which is an orthogonal matrix. Okay? But again, this is only for us because I will need to refer to the vector of wavelet coefficients that correspond to my data, so it's easy to capture it that way. I think I have a couple of examples of wavelets. These are the Haar wavelets, the simplest form of wavelets that we can construct. So in this particular case, the wavelet mother is that function that you see up there, a very simple step function. It's equal to 1 in between 0.5 and minus 1 between 0.5 and 1. And then through J and K, you can construct your family of Haar wavelets by dilating and compressing the mother wavelet and translating it along the real axis. And so you will build your family of wavelets. And now if, say, this is your signal, the signal that you're trying to approximate, this will be the kind of functions, stepwise functions that you use to approximate this function. The wavelets that I'm going to use today are the Dobschi wavelets, which are much more complicated than the Haar wavelets. I'm only going to show you the form, so forget about the blue line, but if you look at the green line is an example of a mother wavelet for the Dobschi wavelets. So you can choose this as a mother wavelet and then again construct your family from here, or you can choose this as a mother wavelet and construct your family, or this or that. And you see that the difference is in the smoothness, right, of the function. Okay? So this is way smoother, so it has more derivatives than this one, but you will also notice that this one here has a larger support, much larger than this one up here. So this one is less compact, okay, in time, it's less localized in time than this one. So typically what we do, we try to look at the data and see how rough or how smooth you think your approximation should be, and you choose the number of the chi that seems to match that. In my experience, the mean values, the 4 to 7, work well in a lot of different situations. Okay, so let's keep on. Okay, so to summarize, in wavelets, you choose your mother wavelet, for example, the chi number 4. You construct your family of discrete wavelets this way, and then on a piece of paper, you would construct a wavelet series of an unknown function f. In practice, because you observe data as observations on your function, you use the discrete version of the construction, to calculate wavelet coefficients. And this is going to be my short notation for this operation. Yes.
Can the Dobeshi's wavelets be parameterized? Can be embedded in a continuous family of?
So there is no formula for the functions that you can write. No, they are constructed in a kind of a recursive way. So there is only an approximation that you can write. Yeah.
But the recursive, they still could be in principle parameterized.
Parameterized, yes, but you cannot write f of x equal, but they can be parameterized. Yes. Yeah. Okay. So. All right, so again, if I get some data, time series data, I can apply a wavelet transformation simply by pre-multiplying the data by this matrix W, although in practice, in a calculator, things happen in a much faster and more efficient way via application of a set of recursive filters, okay? But the end product of this will be a vector of wavelet coefficients, which you can see as a long vector composed by a number of subvectors, each subvector describing features of the data at a different scale. So then, for example, it's easy to think of something like this. So if these are my data, and this is the matrix notation for the wavelet transform, then if I want to write the variance and covariance matrix of the wavelet coefficients, my vector z, then it can be easily derived in this way via the autocovariance function of the process that has generated the data. Okay. And here you can plug in whatever you want. What I'm going to do, since I'm looking at long memory data, I'm going to plug in here a long memory process and see essentially what happens, okay, at this matrix here. And we will see that this matrix is almost diagonal. Okay? And so in that sense, we talk about decorrelation properties. You can have a highly correlated process generating your data, but the vector of your wavelet coefficients will be not diagonal, but approximately diagonal. And so a long time ago, I kind of played with the sort of ideas, and also by looking at the way of calculating the wavelet transform via recursive filters, we also came up with a similar algorithm that would allow you to calculate this matrix using the recursive filters of the wavelet transform, so that you don't have to do this matrix product, because when n is large, this would be a very large matrix to calculate. Okay, so there are ways to do that efficiently. So let's see, for example, what happens if we plug in a long memory process. As I said, I'm going to focus on this discrete time, the RFIMA PDQ models. For this process, we know we can write the form of the autocovariance function that will depend on all the model parameters, and D in particular is going to be the long memory parameter. This is the form of the autoregressive part and the moving average part of the process. Okay? So there are the autoregressive parameters, the moving average parameter, and the long memory parameter, and the innovation variance sigma squared. In this paper from 1992, Sowell gives the form of this autocovariance function. So I can simply, plug in values into the parameters and calculate that function. I'm gonna give you the example with the simplest of these models, which is the ID process. And so in that case, the autocovariance function simplifies to the form that you see up here. If you look at this paper by McLeod and Heipel, they give a simple method that you can use to generate a time series with long memory properties from the ID process, and which uses the Cholesky decomposition. So this is essentially what we followed. And again, as I said, I'm just going to show you the decorrelation properties of the wavelets just on a plot. So essentially what we have here, this is for the Arfima 1.21, because I thought I had the Arfima 0.1. Okay. For the full model, the Arfima 1.21, what we have here is a plot of the matrix, the variance and covariance matrix of the wavelet coefficients obtained for R wavelets and Dobschi wavelets with number 7. We call them vanishing moments, so with 7 vanishing moments. Okay. So going back to what we had here is the plot of this matrix here, okay, for 2 different choices of the wavelets. Okay. And when you kind of generate your data from an Arfima model. And so when you see white is 0, essentially, okay? And when you see black is not. And you can see that if you increase the number of vanishing moments of the Dobschi wavelets, you get a sparser representation or a less and less correlated vector of wavelet coefficients. Again, remember though that you lose some other of the properties of wavelets, which is the localization in time. Okay, so we refer to this as the decorrelation property of the wavelets. Again, just show you something very, pictorial and anecdotal, but there are, if you go through the literature, early 90s or so, I think this, has been fully exploited. Okay, there are a lot of results on this, more formal results. And the sum of the literature is up here. Okay. For continuous time, fractional Brera motion for discrete time, and for Arfima models. So then how can we use this idea? So as a statistician, it's appealing, right? Because you have something which is highly correlated in the time domain, and then you take a wavelet transform, and things simplify a lot in terms of the correlation structure. And so this has been exploited by a number of different people. I'm just going to show you my work from a few years ago, where we used this idea in a Bayesian estimation method for Arfima processes. But again, there are a lot of contributions in an area which I believe is by now fully exploited. So for example, if you want to be Bayesian and you're trying to estimate the model parameters from an Arfima, then you can take the wavelet transform of your data. Again, in the wavelet domain, you can assume a very simple model. Essentially, you assume this matrix to be diagonal. Okay, we have seen it before that it is almost diagonal. And so then practically you have, if you assume Gaussianity, of course, you have the IID assumption in the wavelet domain. And then if as a frequentist, you can estimate the parameters in a frequentist way. As a Bayesian, you would put priors on the parameters, and with very simple priors, kind of like, you know, uniform priors on the long memory parameters and on the other model parameters. It's very easy to do inference. You can also do inference. The integrated ID case, you can do inference in closed form, so it's just very straightforward. And you get estimates of the model parameters in the wavelet domain. So here, for example, we have for two different lengths of the data, 2 to the 7, 2 to the 9, at different values of the long memory parameters. We looked at the estimation results on D. For the case of IID data in the wavelet domain, so a fully diagonal matrix, we also looked at the results that we would get by not making their assumption, so by using the full variance and covariance matrix in the wavelet domain, and also the estimation results that we would get by an intermediate case, which is a block diagonal. So essentially using also these block diagonals that you see in this. So everything which is not non-zero, essentially. Okay. And you can see from the numbers, the results don't change much. So really, the assumption that you make in the wavelet domain seems quite reasonable. And the numbers in parentheses are biases, okay, because we repeated this a certain number of times. Okay, so we also looked into the estimation of change points in the long memory parameter. If you look in the literature on change points, in particular the literature in the econometric literature, there is a famous paper by Chib and Siddhartha Chib and Greenberg, I believe. Should double check this. So where they proposed this Bayesian model for the estimation of change points in a parameter. So we have applied it for the long memory, but it's certainly, the technique is certainly quite general. And so essentially you assume that there is a certain number of change points in the long memory parameter, and you want to estimate the location of the change points and also possibly the number of them. Again, the idea is to do the estimation in the wavelet domain, so that under the Gaussianity assumption you can work with IID data, which simplifies the way that you write the likelihood. And then again with the prior framework, which is quite straightforward, just as uniform priors on dk, a uniform on k, the number of change points, and essentially a non-informative prior on the location of the change points. It's relatively easy to implement an MCMC method, a simple MCMC method if you are willing to fix k, the number of change points, or a reversible jump MCMC if you also want to estimate the number of change points. Okay. So again, the Bayesian machinery is kind of standard down here. So then we can estimate the number and the location. So on simulated data, again, from 3 different types of our FEMA processes, what you have here is the posterior distribution of k, the number of change points, being either 0, 1, 2, or 3. And so you see that the max is for 1 in the 3 cases. And then for the FEMA 1D1, so given that the max is a 1, you can estimate where it is, okay? And the 2 values of the long memory parameter and also the values of the other model parameters. Everything comes from the MCMC. Okay? And in the paper, again, a few years ago, so in the paper we looked at the famous benchmark example in the long memory literature is the Nile River, the yearly minima data set. Which is believed to be long memory with a change in long memory behavior at some point. So if you run the machinery, again, the Bayesian estimation in the wavelet domain, we got indeed that there was one change point, which was at roughly here. Oh yeah, at 726 AD. Okay, so roughly here, and this would be the posterior estimate of the long memory parameter before and after the change point. Oh, all right. Again, I think it's a method which is now standard, at least in the Bayesian literature, for the estimation of multiple change points, which will be readapted to the wavelet domain. Okay, so now I move to the last part of the talk, which is closer to what I'm doing right now, which, as I said, is it's a model, it's a Bayesian model for the estimation of fMRI data, and I'm going to use some of these ingredients. In particular, we'll be looking at a regression model where the error term will be long memory, and so we'll take a wavelet transform to simplify my inference. So this is going to be the model, yi equal to xi beta plus epsilon I. Yi is going to be my n times 1 response data, which is going to be an fMRI time series from a single voxel. At least I'm going to write the model voxel-wise. Now we're going to estimate multiple voxels at some point. But the model is written voxel-wise. So you have a voxel-wise fMRI time series. X is the design matrix. We're going to be in a situation where the subject has to be looking at a screen. There is something going on in the screen, and so we want to watch his reaction to that. And so X is going to be the stimulus time course to when there is something going on versus when there is nothing going on. And then beta is the regression coefficient vector, which measures the strength of the response corresponding to the given stimulus. And I'm going to argue, actually it's not me arguing, but if you look in the fMRI literature, people have been using error types which were autoregressive. There's a famous software SPM where the standard model is fit with an autoregressive model, but if you look in the fMRI literature, there is kind of a lot of evidence and arguments for having a type of long memory error in that model. So we are going to do that. Again, the inferential approach is straightforward. Once you move to the wavelet domain. So again, these are going to be my data. This is going to be a long memory error. And so what I'm going to do, I'm going to take a wavelet transform of my data, which means also that I'm going to take a wavelet transform of this part of the right-hand side of the model as well. Okay? So after that operation, after the wavelet transform, then my regression model would transform in another regression model in the wavelet domain, where I'm regressing wavelet coefficients on a transformed stimulus matrix. Okay? And also my error term is transformed into something which I know I've given you evidence before, something that I can consider diagonal error. Okay? And so again, I'm going to assume that this matrix will be diagonal, okay? But the diagonal elements of this matrix depend on the long memory parameter and all the model parameters, so I've not lost anything. And so again, in this framework, in the wavelet domain, with again relatively simple priors on D and the model parameters. Again, the Bayesian machinery is standard here. We can just do an MCMC with Gibbs steps on beta and sigma squared and the metropolis on D and learn on the parameters. Okay? And we're going to have an estimation of beta, the effect that we are looking at, and also an estimation on the long memory, and also an estimate of the variance. So the model parameters don't change in the wavelet domain, right? Which is important. They have the same interpretation. I'm going to show you an example from a very simple experiment. It's a kind of a benchmark data set again up there. In fMRI experiments, so with fMRI we measure changes in neural activity by detecting associated changes in the blood flow. So the technique uses blood flow oxygenation level contrast to detect changes in the regional cerebral blood flow. And so essentially we have, in the experiment, I think we will have a subject looking at a screen. There is something going on in the screen, which is the stimulus, and the machine measures the change in blood flow in response to that stimulus. Now, because of the way that the experiment is done, there is a delay, right, that we need to take into account. And people refer to this as a hemodynamic delay between the change in the blood flow and the stimulus. And so what people often do, they measure this delay by a hemodynamic response function. And here today, I'm just going to use the most common function used, which is the Poisson response function. I'm going to fix the parameter at 4. Okay, so essentially, after convolution with this hemodynamic response function, the model that I'm going to use is, again, this linear regression model where Y is the observed fMRI signal at a single voxel, X is the convolved, is the design matrix of the convolved stimulus, which again takes into account this hemodynamic delay in the experiment, and epsilon is going to be long memory. I think I already said this, right? Usually the residuals are assumed autocorrelated, and the standard choice is an autoregressive model, oftentimes with just leg 1, and it's this standard choice in this very famous SPM software that everybody seems to be using in the field. But if you look into the literature, there are some people arguing for long memory processes, so for the autoregressive not being a good representation of the error term. And there are some people who have been using statistical models with this sort of error terms, also exploiting, like I'm doing here, these decorrelation properties of the wavelet transform. I'm going to show you data on simulated data. Instead of going through this slide, I think I just show you this. So in simulating the data, what we do, we first simulate a zero mean periodic square wave signal, which represents the stimulus, right? Something is going on here versus not going on, and so forth. And then we're going to convolve that with that Poisson hemodynamic response function that I was telling you about, getting the convolved stimulus, which is this. And then to this, multiplied by beta. And then to this, we add the long memory error term. Okay? So these are our simulated data. And the long memory was the integrated process. So then if you run that Bayesian machinery in the wavelet domain, again, the MCNC will give you estimates of D and estimates of the parameters. And here we have MSC results over 100 replicates. We looked at different values of the long memory parameter, different length of the fMRI signal. These are the results in terms of estimation on D sigma squared and B. Okay, so pretty good results all throughout, I believe. For real data, we use this epoch data set which is provided by the Wellcome Department of Imaging Neuroscience. It's available in SPM and on their website. They have a very, very nice website with a lot of data. It's from some time ago. It was originally collected by these two people, and it has been analyzed by a lot of people. It's a very simple experimental design. There are indeed 4 conditions: fixation, attention, no attention, and stationary. But like most of the people have done, we have grouped the 4 conditions into 2 categories so that you have the 0-1 design. And so it's so all the attention conditions are grouped together, and the 0 otherwise. And so one subject looks at a point, a fixation point in the middle of a transparent screen. In the fixation condition, the subject sees only the dark screen except for the visible dot that doesn't move. And then in the other condition, something happens on the screen. There are 250 white dots that move rapidly from the fixation point in random direction. And different things happen in the different conditions, but again, we have grouped them all into something happens on the screen. We have, these are a lot of technical details. I don't think we are interested in those, but the experiment is actually 4 runs of 5 minutes and 22 seconds for each condition. This is the details on the actual machinery used. We get 400 weighted fMRI images, so 100 images for each run. But then I think there is the first 10 in each run that were discarded. They're usually discarded in this experiment. So altogether, we have 360 image volumes, which is the length of the time series. And we have a lot of voxels because we have 32 contiguous multi-slides covering the entire brain. Okay? And what I'm going to do, I'm just going to show you results on 3 of these slides. Okay? So each voxel has so we have 32 contiguous slides, and each voxel has, for each voxel we have a time series of 360 image volumes. Okay, as I said, we convolve the data with the Poisson hemodynamic function with lambda equal 4, arbitrarily chosen. I'm going to show you the results for 3 slices. At least 3 regions of the brain which are supposed to be implicated in attention, okay? Which is what this experiment is about. These are the activation maps for the betas. So we fit the model voxel-wise, right, on each voxel of each one of these 3 slides. And then you get from the MCMC, you get the estimate of the beta, the posterior mean, and then you can just collect these estimates to form the image that you see up here. Okay? And what we have here is our method on the first row, and the second method is the model with the autoregressive noise, so ignoring the log memory part. If you look carefully at the images, you can see that indeed the log memory noise estimation seems more precise. The regions that you have to look at are those up here, which you see are slightly lighter, okay? And they seem to be more localized on the correct, on where you would expect the signal to be, the activation, okay, to happen. Okay? And also, because the approach is Bayesian, so we get posterior probabilities. So these are the estimates, right, of the beta parameters of the strength of the association. But we have a posterior probability for that, so we can show what we call posterior maps of activations, which we get by thresholding, in some sense, the posterior probabilities. And so these maps here would give information on the regions on the slides which are likely to be activated with a certain confidence, which is given by the posterior probability. So again, this would be the regions of main interest. And again, as I said, this is a benchmark data set, so other people have been looking at this data. They seem to find consistent results, also in terms of the autoregressive model not being precise in the estimation. In our model, we also get estimates of the innovation variance. Again, the first row is our method, the second row is the model with the autoregressive noise. So you see that with the autoregressive noise, a lot of what could be signaled ends up in the error term. And with our method, because we assume the long memory parameter, we also get for free estimates of the long memory parameter, although nobody would know how to interpret those estimates for us. I mean, what does it mean that there is long memory? So it's hard to attribute the long memory to neurophysiological events. At least this is what they told us. Okay, so I've tried to give kind of a circular talk where I started talking about wavelets and the correlation properties of wavelets, in particular for long memory data. And I show you some evidence of that on discrete time fMRI models. And then we also saw a method for the estimation of change points in the long memory. And then I've used some of those ideas in this regression model with long memory errors, which we have developed for fMRI data. That was that model that I just described. The paper appeared in Biometrics last year. It was just our very first attempt. And if you are an expert in fMRI, you will recognize that as kind of a very simple model. Okay? And so right now we are exploring a better model in some sense, where instead of fitting the model one voxel at a time, we try to do it subject-wise, or at least multiple voxels at a time, which allows us to incorporate priors for the selection of the activated voxels. And also we have abandoned that idea of thinking that the hemodynamic response function is given, and now the estimation of that function is incorporated in the model. Okay? But this work was kind of getting me towards too big of a tangent with respect to the topics of the workshop, so I've left it out. But the paper is in revision with the journal Neuroimage, so hopefully we'll get it there at some point. Okay, and that's all I have. Thank you.
Are you familiar with the work of Lai and Xing? Lai and Xing claim that if you have a short memory Gaussian process with changes in the mean level, that you can't distinguish it from long memory.
It could be equivalent, yeah.
Is that a correct assessment, or you think it's nonsense? Or?
I don't know, so I've not tried to fit the other model, but I remember, so at the time of the biometrics paper, one of the referees argued that way, and eventually we got by with it, but I think it would be interesting to compare, because a lot of fMRI people would argue that, right? That you can equivalently capture that phenomenon through the mean. I haven't done it, but it would be interesting to compare the two models, yeah.
And I had a couple more questions. I only tried a little bit to understand what people do with hemodynamic response, but I had the impression that there's somehow supposed to be a reaction, so that there's actually a little negative tail following the positive mode, but yours doesn't have that property.
No, here, no, because we use the Poisson, but there are other forms of hemodynamic response functions that account for that. And so in this model, we didn't do, and you just trust your Poisson function. But in the current model, we're looking at least 3 different forms of that hemodynamic response function. There is a huge literature there. Yeah. Yes.
Is that response function assumed to be compact?
Complex.
Compact.
Compact, that is
Yeah.
supported by a finite interval.
I don't know, Hernando.
Yeah, it has to
Is it? It has to be.
Otherwise it goes up.
Yeah. So there's kind of a nested idea, isn't
Oh, yeah, okay. But, oh yeah, I mean, with the Poisson it wouldn't work that well, but yeah, no, you're right, yeah. Interesting, yeah.
Even just a little comment on your current work here. One work that appeared in JAS recently also is that you can look at the entire 3D brain, right?
Oh, wow.
But then if you look at the spatial temporal covariance structure, it's very, it's prohibitive. And so what the people have done was they did a Fourier transform of the time series at every voxel. So as a decorrelating step, just like your
Okay.
Wavelets here.
Okay.
And therefore, they came up with a spatial spectral covariance structure. So I think might be applicable to what you're.
Okay, interesting. You just said it has appeared in JAS, huh?
Yeah, 2012.
Okay, I'll look for it.
Any other questions?
Just a quick question of point of fact. When you looked at the fMRI data for the attention task, what was the length of time over which that lasted?
Was it 360, the time series, right?
360
Yeah,
what?
yeah, points. In
Yeah,
time.
360 points, but what in time terms is that?
Does it say? I thought it was 4 minutes and something. 4 runs of 5 minutes and 22 seconds for each condition.
Okay, so it's about, so each run is 360 points?
Yeah.
4 minutes is 360?
No, that's the entire thing, right? Because each
So
run,
four
for 100, oh, each run gives 100, sorry. Yeah, 100 images for each run. So how much would that be?
So 322 seconds
Times
Times 400.
400, yeah.
So you've got time in that for plenty of heartbeats, heart pulses, yeah? I'm just wondering how you allow for that.
Yeah.
External rhythmic driver.
Yeah, no, it's possible. I don't think maybe not for this data set. It's quite old, but I think they collect also this sort of data, so it would be nice to integrate the. But I don't
within
know.
Because you're measuring something which is affected by blood flow.
Sure, the heartbeat is going to be, yeah,
is going
that's
to be a
very nice,
constant
yeah.
presence in your data.
Yeah.
Not particularly, because it's actually it's the blood entering your brain is designed to actually smooth out the heartbeat. So in neuroimaging data, there's very little heartbeat effect.
I see.
So you don't have to worry about it. There are other things that you can include as regressors and just regress them out, but heartbeat is not to worry about too much.
Thank you.
Any other comments, questions? Not? Please join me.
Thank you.